Hey, Stat200. This office hour I'm going to be talking about confidence intervals, something we use to estimate a population parameter. So before I get started, I'd like to just hit this over and over and over again. This will trick many of you. Without getting into a philosophical discussion about statistics, just remember that for this course, population parameters do not vary. Okay? So there will be a few questions that ask, which one is likely to vary, or if you change this, what's going to happen, and we'll have a choice between the statistic varying and the parameter varying. And I want you to remember, population parameters do not vary. In this class, they're considered fixed. There's one true mean height, for example, for American men. It's a fixed height. We don't know what it is really, but we know that it's fixed. Doesn't vary. If you take a different sample size, that parameter stays the same. You see what I mean? Just try to remember that. That catches a lot of people off guard. Alright, let's jump into some example questions. So, suppose that a confidence interval for population proportion P is to be calculated. For a sample size n equals 60 and sample proportion P hat equals 0.35, what is the approximate margin of error for a 95% confidence interval? Alright, so we're going to have to remember this one. This is a very important one. When we make a confidence interval, it's composed of basically three parts. So we'll have the point estimate, so we're looking at parameters here. Proportions here. So we're going to do this in the context of proportions. So we're going to have the confidence interval is going to be P hat plus or minus Z star, and we're going to talk a little bit about Z star, times the standard error. So we'll call that, okay, we'll multiply by the standard error. Okay, so these are the three parts, basically. And this, in particular, applies to proportions. Now, we're asked to find the approximate margin of error for a 95% interval. The margin of error is going to be this bit right here. That's going to be the margin of error. So that's what we need to find here. Now, we're getting a nice softball here. It says 95% confidence interval. You can use, if you want to be more precise, you can say that Z star, which is the multiplier, you use the table for that. You can say that it's going to be equal to 2 for a 95% confidence interval. It's approximately equal to 2, which means all we need to find, really, is the standard error. Now, quick note, this Z star, this multiplier, basically tells us how wide or how narrow our interval is going to be. Basically, how confident we're going to be that this interval we're creating is going to contain the true population parameter. Notice how in this formula here, I've got no population parameters. P hat is a statistic. This right here, the multiplier, comes from a table. The standard error is calculated from the statistic. Right? It comes from P hat and it comes from the sample size. So we're using all of this stuff that we get from the sample and we're trying to apply it to the population. And this multiplier right here is a result of looking at mathematically what we're looking at with the normal distribution. And if you'd like to learn more about that, please feel free to give me an email. So let's go through and calculate this. Z star, we're going to say, is approximately 2, because it's 95% confidence. And if you remember from the empirical rule, the 68, 95, 99.7 rule, that means for 95% confidence, we have 2 standard deviations from the mean. So what's the standard error in this case? The standard error is calculated like this. It's going to be the square root of P hat times 1 minus P hat divided by the sample size, n. And in this specific case, P hat is 0.35. 1 minus P hat is what? 0.65. 0.65. Sample size, 60. Right? So we're going to plug that into a calculator, and the answer we're going to get is going to be approximately 0.0616. 0.0616. Okay? So that's our standard error. So let's just remember that's the standard error here. And now to find the margin of error, we talked about it before, we have to multiply by approximately 2, right? And we don't really need a calculator for this. This is pretty easy. So the margin of error, the MOE for brevity, is going to be approximately 2 times 0.616, which again is approximately, let's see, 1.32. Am I doing that right? Let's see. Oh, sorry about that. That is not right. I missed a digit in there. Should be 1.232. Just about. So that's what you're looking for. That's the answer there. 1.232. And that's how you find it. Let's move on. Many undergraduate students are thinking about getting a graduate degree. Do male and female students have equal opinions about this? A survey of undergraduate students at public universities in the state of California revealed the following results. Out of 265 female students, 131 were seriously thinking about applying to graduate school. Out of 233 male students, 130 were seriously thinking about applying to graduate school. We wish to compare the proportions of male and female students who are thinking about getting a graduate degree by calculating a confidence interval for the difference between males and females. What is the correct notation for the parameter that is estimated by the confidence interval? Let's pay attention to the actual question, that final line there. What is the correct notation for the parameter that is estimated by the confidence interval? And we can immediately go ahead and cross 2 of these options out. I'm going to cross out this one and this one. Why? Because those are not parameters, right? X bar and p hat are statistics. They're not parameters. So if you see X bar or p hat anywhere, you know that can't be a parameter. So now we're down to mu1 minus mu2 and p1 minus p2, or I guess it's actually rho 1 minus rho 2, if you're into your Greek letters. I'm going to call it p for simplicity. Okay, so are we comparing a mean, or are we comparing proportions? Easy. You just go up one more sentence. We wish to compare the proportions. Well, that narrows it right down. Can't be means. It's proportions. And that's how we find our answer. This is really just to kind of keep you thinking about what these symbols mean. Mu, that Greek letter, is short for mean, a population mean. It's a parameter, population mean. X bar is a sample mean. P hat is a sample proportion. And P, or rho, either way you want to say it, is the population proportion. That's a parameter. Okay? Any questions about that? Send me an email. Let's move on. If the sample size n is large, and the sample is a random sample, then the distribution of the sample proportion p hat is approximately a what? Alright? Well, what do we think here? This one's tricky because I don't think many people really grasp the notion of these distributions. This is something that may serve you to simply memorize. Alright? The sample size is large. The sample is a random sample. The distribution, now we're not talking about the distribution of individuals, we're talking about the distribution of the sample proportion, p hat. So this is saying if we took multiple samples over and over and over again, then the proportion is approximately what? It's not binomial. This has to do with the central limit theorem. It's not uniform. It's what? It's normal distribution. Normal distribution is kind of the magic distribution, right? If we're talking about distributions that really made a difference in statistics, normal distribution above all is going to get a lot of credit. So the normal distribution is that bell curve that we always use. And what the importance of this question is that the central limit theorem states that if you basically take samples over and over and over again, and you look at the parameter, so it doesn't matter if you're interested in the means or the proportions, they will eventually approximate the normal distribution. Where those proportions or those means lie will resemble the normal distribution. Now, in the case of means, we actually have an interesting kind of issue that comes in numerically, and the best thing for you to remember there is that when we're discussing means, we're going to use the t distribution. We're discussing proportions, we can stick with the normal distribution, which is often shown as z. So the answer here is normal distribution. I'm going to get that out of the way. The binomial distribution doesn't work because the binomial distribution only works with discrete variables. Okay, so that only works with variables that can have values 1, 2, 3, but it can't be 2.5 or 0.356. Now, a sample proportion p hat is going to be between 0 and 1, so it definitely can't be binomial distribution. The uniform distribution is actually worse. I don't know if it's actually talked about in the notes very well, but the uniform distribution looks like this. If we're talking about a proportion, then the chance that the p hat is between 0 and 1 is uniform. And what we mean by that, now imagine this is the bell curve over here. So this says, likelihood kind of goes up, and it's like peaked in the middle right around the true value, and then it kind of slumps off, right? It makes a lot of sense. The uniform distribution is a solid line. So imagine this sombrero is instead just a flat board. That's the uniform distribution. If that doesn't make sense, that's fine. Main thing to remember, as you take repeated samples, then the distribution of the sample proportion going to be normal. Again, more questions? Send me an email. I'm ready for them. All right, here's a good one because this is going to come up multiple times in this class. I guarantee it. You're going to actually construct, or basically find the ingredients to construct, a confidence interval. So this says the cholesterol levels of a random sample of 100 men are measured. The sample mean is 188 and the sample standard deviation is 40. Which of the following provides a 95% confidence interval for the population mean? Right? Now, important thing to point out. We're looking at a confidence interval for the population mean, which means we're looking at the sampling distribution, which means we're not going to use standard deviation by itself, we're going to use standard error. So, that's basically what we're being quizzed on. Remember I showed you before we have that kind of formula for putting together a confidence interval? I showed you the one for proportions. This is one for means, and it's very similar. So the basic formula for means is x bar plus or minus. Now we're not going to use z star, we're going to use t star, and we're going to multiply by the standard error. That's the basic formula for a confidence interval for means. So we already know where x bar is coming from, right here. Sample means 188. That's where that goes. T star, well, we're going to look. I'll show you where it comes from in the table, but we already actually know that it's 1.99 because it's invariant on all these options that we have. So we know that that's going to be 1.99, and I'll show you where that comes from. But the standard error, that's what we need to figure out, right? We talked about that already. So the standard error is simply the standard deviation. So let's talk about that. Standard error is the standard deviation divided by square root of the sample size. In this case, our standard error is 40. Our sample size is 100. Square root of 100 is 10. That's going to be 40 divided by 10. 4, right? So that makes it very clear which answer is correct. X bar we know is 188. T star, well, they're all the same, so we don't have to choose. The standard error is 4. So it's got to be this one, right? Now that 1.99 comes from the following. We have a sample of size 100, and we're going to do a 95% confidence level. So let's look at this table. Here's a sample of size 100, right here. Sample of size 100. Now, an important thing to note is when we're looking at the t-distribution, we have to take into account degrees of freedom. Degrees of freedom, or often I'm going to just approximate or abbreviate them, df, are equal to the sample size minus 1. So if we have 100 in our sample, and we decide to subtract 1, that means now we have 99 degrees of freedom. And look, this column, right here on the left side, has degrees of freedom. And it starts at 1 and it goes all the way up, and then it starts to jump. Once you get to 30, it goes 1 to 30, and then 40, 50, 60, 80, 100, right? So, we don't have 100 degrees of freedom here, so we can't quite make it here. Notice that these numbers, the further down, the smaller they are. And that's because it's saying, oh, you have more information now, so you can make your interval, your guess, more precise. You can shorten that interval. But you have to be conservative as a statistician. You can't just jump ahead and say, you know what, I got this. We have 99 degrees of freedom. It's really close to 100. It's closer to 100 than 80. Let's just go with this, right? Can't do that. As a statistician, you always have to round down. So if you have 99 degrees of freedom, as we do in this case, the next best thing you can do is use 80 degrees of freedom. That's all we have in this table. Now, software and other tables may have different levels of degrees of freedom. This is going to be the standard table we're going to use in this class. So I'm telling you now, this is how you're going to need to use it. 99 degrees of freedom means you have to use the line for 80 degrees of freedom, because it's the next lowest. Okay? Now, you'll notice the columns here have confidence levels. It's as simple as that. Question tells us to use 95% confidence, so we're going to stay in this column here. So, given everything I've said, we've got 80 degrees of freedom in the 95% confidence column, so that's why it's 1.99 and not 1.984. Okay? So that's where that comes from. I hope that's clear. And again, questions? Send them to me. Let's move on. Suppose that a confidence interval for a population proportion p is to be calculated. For a sample size n equals 100 and a sample proportion p hat equals 0.50, what is the approximate margin of error for a 95% confidence interval? Again, I'm going to just draw or write this formula again. Right here we have p hat plus or minus z star times standard error. And the margin of error, right here. Margin of error. That's what that is. Okay. Now, we talked about it last time, and this is the most common confidence level because it's easy to approximate. 95%, you're going to say this z star is approximately equal to. So now we just need to calculate the standard error just as we did last time. So we're going to do 0.5 times 0.5 divided by n. What's n? 100. Right? Well, this is actually pretty easy because you have basically 0.5 squared in the numerator here, right? 0.5 times 0.5, that's 0.5 squared. You're taking the square root of a square. So that's going to be, I'll show you how this simplifies. That's going to just equal 0.5 divided by, what's the square root of 100? We're in the denominator now. What's the square root of 100? 10. Right? So, here's 10. 0.5 divided by 10. Well, that's easy. If you divide 0.5 by 10, you're just going to add another decimal in there, right? Or another 0 between the decimal place and the 5. This is going to be 0.05. Now that is not your margin of error, right? That's your standard error. That's all I calculated. So here's standard error. Let me just write that for clarity. That's the standard error. The margin of error is going to be 2 times our standard error is our margin of error. 2 times 0.05 is what? 0.10. Alright? That's where that comes from. And this one's thrown in here to get anybody who's being overeager. Okay? Moving on. Based on the 2000 census, 31.8% 96% of grandparents in California are the primary caregivers for their grandchildren. Suppose n equals 1,000 persons are about to be sampled from this population, and the sample proportion of grandparents as primary caregivers, p hat, is to be calculated. What is the mean of the sampling distribution of p hat? Okay. Key thing to remember here, a census is everybody, right? I'm sure you guys all know that. So a census doesn't give us a p hat. This 31.8 isn't a p hat, that's actually p. So we know that p is equal to 0.31880. And now here's the key concept. The mean of the sampling distribution of the statistic, this is p hat, this isn't p, this is p hat that we're talking about. The mean of the sampling distribution is always going to be the population parameter. That's why we use sampling distributions, because they are a good way to approximate this. Since we already know this, we know what the mean of the sampling distribution is going to be. It's going to be this, 0.318. You don't even have to do any calculations. It tells you. Here's the population proportion. The mean of the sampling distribution is the population proportion. That's it. Simple as that, right there. Okay, next one. For a randomly selected sample of n equals 36 men's heights, it is reported that the standard error of the mean is 0.5 inches. 3 of the following statements are true, while 1 is false. Which statement is false? These are always tough questions, right? Always tough questions. So I like to go through one by one and figure out which one, whether this one is true or false. If you find what you think is a false one, you put that one on the side and you keep reading. And then you see if you have 2 that you think are false, you have to compare them. So let's get to it. The standard error, 0.5 inches, is an estimated value of the standard deviation of the sample mean. That is a perfect definition of standard error. It's definitely true, and if you were unclear on what standard error was, memorize this sentence. It will really help you. You don't even have to include the 0.5 inches, but if you say the standard error is an estimated value of the standard deviation of the sample mean, perfect. Okay? So that one's true. That one's not the false one. If a new sample of n equals 36 men's heights is collected, the standard error of the mean might not equal 0.5 inches. Well, let's see if that's true. The standard error is given by the formula. So SE equals SD divided by the square root of n. Standard deviation. Now, standard deviation is a statistic. So sure, if you take another sample of the same size, you may have a slightly different standard deviation because you'll have 36 men who are maybe not exactly the same as the other 36 men with different heights. So the standard deviation could change. The sample size is remaining the same, but the standard deviation could change, which means this standard error can change from sample to sample. We just use it because we only want to take one sample and we want to have a pretty good estimate of how much each sample is going to vary from the other. Okay? So again, this one's true. This one's true, and here's why. Standard deviation could change, which means standard error could change. Let's look at the next one. Over many different samples of n equals 36 men's heights, the average difference between the sample mean and the population mean will be roughly 0.5 inches. Again, that is true. That is true, and this is a good interpretation of what the standard error is, right? So this says the standard error is 0.5 inches. Another way to think of it is it's the average distance, the average difference between the sample mean and the population mean that you're looking for. So another good thing to keep in mind, that is true. So of course, I've said that those top 3 are true, which means what? This one has to be false. So let's read it and I'll discuss why it's false. In about 95% of all samples of n equals 36 men's heights, the sample mean will be within 0.5 inches of the population mean. That's not true, right? So the difference between the third statement and the fourth statement is that in the fourth statement, we're talking about 95% of all samples. Now that's going to be true of the margin of error, but this isn't the margin of error, this is the standard error. So if this had been changed to be, instead of within 0.5 inches, it said within 1 inch, because it's 0.5 times 2, which is the z star value for 95% confidence, that would have been true too. But it's not. That's not what it's saying. So actually, if you change this 95 as well, this is another way to do it. If you change this 95% to a 68%, it would still be true. Then it would be true again. But as it is, it's not true. In 95% of all samples of n equals 36 men's heights, the sample mean will not be within 0.5 inches of the population mean. Okay, and you can cite the empirical rule as the reasoning for that. You could say, well, the standard error is the average difference between the sample mean and the population mean. That doesn't mean that 95% of them are all going to be within 0.5 inches. Then it wouldn't be an average, right? That wouldn't be a very good average if 95% of them are within 0.5 inches. So this is the one that is not true. Again, that was a little confusing, but it's a really good definition-based question. It really shows that you understand the intuition. And if you watch this, just keep what I said in mind. All right? That'll actually help you a lot in these upcoming quizzes and the midterm. All right. In a past general social survey, they call them GSS, a random sample of men and women answered the question, are you a member of any sports groups? Based on the sample data, 95% confidence intervals for the population proportion who would answer yes are 0.13 to 0.19 for women and 0.25 to 0.33 for men. Based on these results, you can reasonably conclude that one of three things. Well, let's talk about what we can conclude here. So we're looking at confidence intervals, and we're pretty sure that the proportion for women is between 0.13 and 0.19, right? That's where women are. So let's just draw this all in a number line. Here's the number line. Here's 0.1, and let's say here's 0.35. Ooh, that's a terrible point. You know what I'm talking about. Okay. So it says that women are about between 0.13 and 0.19. Okay? That's their confidence interval. Men are between 0.25 and 0.33. Now, do those intervals overlap? No, they do not. The whole women's interval is below the whole men's interval. So what we're talking about in this lesson is if you have confidence intervals and they don't overlap at all, you can conclude that those two groups are different. So let's see where that says that in the answers. It says at least 25% of American men and American women belong to sports clubs. Well, you can't conclude that, right? Because American women are all below, like the whole confidence interval is below 25%, so that's definitely not true. There is no conclusive evidence of a gender difference in the proportions of men and women who belong to sports clubs. No, actually, this is the conclusion you'd reach if there was an overlap. So if the upper bound for women was over here and the lower bound for men was over here, you'd say there's no conclusive evidence for gender difference. That's what happens if they overlap. But here, this is obviously going to be our answer, there is conclusive evidence of a gender difference in proportions of American men and American women who belong to sports clubs. It's exactly what we concluded before. I find that the number line is easy to visualize what's going on. You can see that the proportion of women is estimated to be entirely below the estimated proportion of men. So we say, hey, there's a gender difference. There are more men in sports clubs than women. All right? With 95% confidence, as always. Okay, one more. This one I have taking up a little bit more room by itself because I had to get these Z tables on here. This is going to be a confidence interval building sort of example. In a survey of 950 randomly selected individuals, 17% answered yes to the question, do you think the use of marijuana should be made legal or not? a 98% confidence interval for the population of all, for the proportion of all Americans in favor of legalizing marijuana is what? Now this is hard. You can't just simply guess because it's really hard to tell, right? You have to multiply things. So, looking at proportions. Do you remember that skeleton formula that I gave for proportions before? I'm going to write it down again. It's p hat plus or minus z star times the standard error. So let's plug these in one by one. P hat is what? 0.17. Plus or minus z star. Ooh, alright. So here's the tricky thing, because normally we do 95%, but this is actually 98%. Alright? That's tricky. So here's what we're going to have to do. This table, these are actually two sides of the same table. One has negative values and one has positive values. And what we're looking for here, and what this table gives, is to visualize, is it gives the area, so the total area underneath the normal curve needs to be equal to 1. Now what this table gives is if you have a z value right here, it will tell you how much area you have in here. So that's the proportion. This is the probability of proportion right here. And it gives you that z value. That's basically what this is telling us. Now we want a 98% confidence interval. So what we're looking for, to visualize it sort of in the context of a normal curve, forgive my curve, it's not super symmetric looking, but imagine that it is. What we want is we want to find the value for z such that between z and negative z we have 98% or 0.98. Imagine that's an 8. Alright? That's what we want. Which means if this table only gives us area to the left of the z value, you'll notice that this is only area to the left, we can either look up the z value that corresponds with 99.9 on the left of it, right? Because they'll have 0.1 over here and 0.1 over here. I'm talking in terms of area, right? Total area is 1. If we're going to have an interval that is symmetric, that means we need to find either a z corresponding to a probability of 0.99 or a negative z value corresponding to a value of 0.01. Alright? So I'll show you both, and I'll show you that they both give you the same answer. Now keep in mind this is negative z, so we're looking for a single value for z star, and it's going to be positive, or it could be negative. But to keep consistency, we're going to keep it positive. So the negative z value should have 0.01 to the left of it. And by that I mean, when we look in this table here, we want to find a probability as close as possible to 0.01. And we get it right here. See that? It's 0.0099. That's only one 1/10,000th away from 1. So you would use this value instead of this value because this value is closer to 0.01. Which means we have a negative z here of 2.33. So negative 2.33 is the value for negative z. And I'll show you how to find that same value on the positive side over here. We're looking for the value that's closest to 0.99. So that's going to be right here, because again, this is only 1/10,000th off. And if you look on the left and top, 2.33. So both ways you can find that value. And I should clarify, when I found this value over here, so I used this probability because it's closest to 0.01, and how I got this negative 2.33 from that is I went first to the left and saw that it began with negative 2.3, and then I had to go up the column to the header where it says 0.03. that means at the end of that negative 2.3, I'm going to put another 3. So we see that the z value here is 2.33. We're going to use the positive value here. So now I can write that in my formula, 2.33, and now I need the standard error. So the standard error is going to be, you guys should know this by now, the standard error is equal to the square root of p hat times 1 minus p hat divided by n. What's p hat? 0.17. So we're going to have 0.17 times what's 1 minus 0.17. You can go to a calculator, or if you just know it, it's going to be 0.83 divided by n. What was our sample size? I actually don't remember. 950. 950. Now that definitely requires a calculator. I cannot do that in my head. So go into your calculator, enter that in, don't forget the square root, and when you do, you'll find that the answer is 0.1 or 0.0122. So we're going to say times 0.0122. Okay? So here is our formula for the confidence interval. And now what do? Now we just find it. So we can simplify this a little bit. We can take 0.0122, multiply it by 2.33. So let's do that right now. 0.0122 times 2.33. That's going to give us approximately, so let's rewrite this. It's going to give us approximately 0.028. And we're going to add and subtract this from 0.17. Okay. So what's 0.17 minus 0.0284 or 28? Go to your calculator and you'll find that it is 0.1415, which will round to 0.142. And now you can go back and add it. Add that same value. Add that 0.028 to 0.17, and you'll find the upper bound is this guy, 0.198426. So that's where we get our interval values. Now this plus or minus, don't forget, that means you subtract it to get one of the numbers, and then you add to get the other one. Alright? And that's how you get the answer. So now we have our 98% confidence interval. It's a long process, and I wanted to explain how you do it, step by step. And it's difficult. It's definitely difficult the first time or two that you do it. So if you find yourself kind of stuck, not really sure what to do, don't be afraid to give me drop me a line, send me an email, and we can meet in the virtual office, or we can talk over the phone. We can walk through how this is done. Okay? It's not super easy. Something that takes getting used to. Alright, that's all I have for this week. So good luck on those assignments, and I'm always here for you.